I'll leave that open. Again, there's the food cart out there. All right, so we're talking about stereoisomers, and we started actually with constitutional isomers in like chapter 2 or something. And what is the difference between stereo and constitutional isomers?
Stereo is like the space.
How there's space that, but they're bonded the same, right? Same bonding pattern. Constitutional just means the bonding pattern is different, right? So stereoisomers, same constitution, different spatial arrangement. That's a good definition there. So, did I talk about this slide or did I skip this one? I can't remember how I. What's that? Okay, good. So I'll come back here. This is another kind of stereoisomer. Okay. Doesn't matter which order you really do them in. And these are known as cis-trans stereoisomer. Now, to determine whether or not something is cis-trans stereoisomer, there's actually some confusion about this all the time. My pen is not quite white enough. Hang on. There's always some confusion about this thing. Oh, and again, that purple color is not good. Sorry, I'm just... you let your kids color with your iPad, and then everything's different. So the confusion about cis and trans is, in order to have something be cis or have something be trans, you have to have two hydrogens attached. Okay? And they have to be attached on adjacent or, well, I guess they don't have to be on adjacent, but they're usually attached on adjacent atoms. In a ring, they can be separated a little further than that. But cis means that the hydrogens are on the same side. And the other part of the confusion is people are like, well, what does it mean to be on the same side? Same side of what, right? So what you do is you take a line and you draw it between the two atoms that you're trying to determine whether or not they're cis or trans. And in this case, it's easy because they're on the front, right? I drew the line here. They're either on the same side, that is, same side of the red line connecting the two atoms, or they're on opposite sides of the red line connecting two atoms. So that's trans, okay? Turns out this kind of notation doesn't work if, for example, this was a chlorine, because then cis is what and trans is what. You don't have like a good definition. So we have other ways of determining what the configurations, we'll call those configurations that these atoms are. So based on our current naming system, right, it would be, these are the same. They would be 1,2-dimethyl cyclohexane. And so we modify the naming system by using those terms, cis and trans. So it's either cis, 1,2, right, dimethyl cyclohexane, or trans, 1,2-dimethyl cyclohexane. So let me write that out. Oh, actually, let's be clever. Trans, 1,2-dimethyl cyclohexane. I'm just going to do that because I can't fit it all in there. And that is, of course, without the chlorine there. So let me get rid of the chlorine that I just drew over there. If one was an ethyl and one was a methyl, you would still say, for example, 1-ethyl, 2-methyl, right? But you would say trans or cis in the front of it, just to indicate the relative orientation of the two molecules, or the two atoms on the molecule. Okay. Oh, that's basically what I said. Here's the other place you can have cis and trans, is on a double bond. Okay, so the key, though, is really that there's constraint. Okay, so in a ring, right, I have constraint because the molecule can't break on this end and then rotate around so that this can be at the bottom, right? So we have a constraint in the rotation. That's what allows for cis and trans. If I take butane and I draw butane, I usually draw it like this. Well, not with an eraser. I draw it like that, right? or I can draw it like this. We don't call those cis and trans simply because the molecule freely rotates at that sigma bond or the single bond that's in the middle and rapidly interconverts between the two, and so we don't call them cis and trans for that reason. So the constraint has to be there. The other common place we see a constraint is when you have a double bond. And in double bonds, we have the constraint. Sorry. Had a big Microsoft keyboard come up on my screen. I'm like, what the heck is that doing there? The double bond, we have a constraint because of the pi bond. And if you take two ends of the molecule and you rotate it, right, you have to break the pi bond to get the rotation to happen. So that is another constraint. That molecule on the left, would we call that cis or trans? We call it cis. Why do we call it cis? Yeah. If you draw the line, right, along the constraint now, right, and you look to see where the hydrogens are, they're together down here, so that's cis. Trans, you draw a line on the constraint. I really want to close this, but I hate to leave my food card out here. But if you're hungry at any time, there's suggested donation prices out there. Awesome. She just gave me 50 cents. I'll put it in the cart later. Remind me that it's Sarah. Let's go through my laundry and it'll be really clean. This is trans, okay? So let me try something on you guys, see if this works. I did butane before. This is butene. Which one of those is cis and which one of those is trans? Or are they the same? Bottom one's cis. Do you guys see how? And top one's trans. Do you see how? All right. Again, you draw the line along the constraint and you look to see where the hydrogens are. That's trans. Draw a line on this constraint with the hydrogens there. That one's cis. Okay. All right. Cannot go back. No. What?
So those are two different molecules?
Yeah. So those are two different molecules. So cis-trans isomers usually have very different properties. Boiling points are different. Melting points are different. Solubilities can be different. Even the odors can be different. I mean, just their physical properties are generally very different. And their chemical properties can be different too. Stereoisomers, okay, the kind that we talked about, the chiral isomers that we were referring to yesterday that are mirror images of each other, their properties are all the same except for a few. Okay.
So only a carbon double bond to carbon creates a restraint, and that's 0, 0.
Yeah, that's pretty much it. Carbon double bond to carbon or a ring has constraint. Yeah.
And how come, so pi bonds doesn't allow rotation, right? So
Right.
if we're talking about like a triple bond,
Oh yeah, why doesn't a triple bond have a constraint? Because it's linear. So things can't be on opposites. So like if you draw a triple bond like this, right? Let's say CH3 and then triple bond CH3, and you want to know cis or trans, it doesn't apply because they're all on the same line. Yeah. There isn't opposite sides on that. Yeah. In a weird sense, there is a constraint on rotation between the carbons, but it doesn't affect anything because it has the sigma bonds on either end, and it just like rotates like a barrel. It's kind of weird to think about, but it rotates like a barrel in the middle. Oh, shoot. Okay, I'm going to skip over this one. Skip over this. Okay, let's identify these as cis or trans or neither. Did we do this slide? No? Okay, good. Because I think I lectured on it in the other class, and then I reviewed it in the other class, so I know I've gone over the slide twice, but I don't remember which classes I went over it in.
Because you went all the way to like 5.3 or something.
Uh-huh. Well, I skipped a bunch of stuff in the middle because I just didn't want to cover it at the time, so I covered it in a different order. Okay, so number one, cis or trans? cis, because you draw a line, got hydrogens like this, hydrogens on the same side. 2, cis or trans? It's a little trickier. It's on a ring now, right? So there's a constraint. I have 2 groups. I have 1 vote for trans. Okay, so let's do this. This is a little trickier. So, when you're doing cis and trans on a ring, you have to think, is it on the top side of the ring or the bottom side of the ring? Okay? So, this OH, top or bottom? This OH, top or bottom? Cis. All right, same side. Really, we're worried about the hydrogens, but that one is cis. This top one is cis. What about 3? Trans. Again, draw the line. You can see the visualize hydrogens here and here being opposite sides. What about 4? Trans. Cis? Trans. Cis? We're all trans? We all believe that it's trans? It's trans. Okay. Now, sorry. What about 5? Neither. Even if the groups here and here were well, if the groups there and there were different, it wouldn't be cis or trans because I don't have any hydrogens on that one, right? So if it was a chlorine and a bromine, I can't call it cis or trans. There's actually a whole different nomenclature for double bonds when you have no hydrogens on one side. Okay, so one other thing I want to show you. These rings, like this ring here, is cyclohexane, right? So I'm going to draw a cyclohexane next to it. And we'll try to visualize. I'm going to make this, and it's a top-down view, okay? Oh, sorry, I meant to put that circle on the inside. Be a top-down view. So this OH group, right, is here. And this OH group is here. So looking from the top of the chair, going in the clockwise direction is what I'm looking at. This drawing looks like this. So if you're good at doing that translation, right, you can see that it's cis because you know that the hydrogens sort of immediately are on the bottom side of that. That makes sense? So sometimes drawing it a different way, if you're good at interconverting between the drawing styles, is a good way to determine whether or not cis or trans. The other way to draw it is this Haworth. It looks like this. Remember, in these diagrams, these come out to the front, so you'll sometimes see them drawn like this, for the wedge coming out to the front. So that whole bottom part of the wedge is sticking out of the board, and this is all going back into the board. Again, if I put an asterisk, I'll put an asterisk here. In this style of drawing, it's like this, and this is an OH up here, and that's an OH here. So those styles of drawings actually show easier what cis and trans are. If it's trans, one of them will be up and one of them will be down. Okay? So for example, trans on number 4, I'm just going to make a cyclohexane. And make that the, put an asterisk there, and I don't know, just for fun, let's put the asterisk down here. And I'm looking down, right? So this group that's here on the asterisk, which way does it go? Out, so towards me. And then if I go on this ring and I'm going clockwise like this, right? I'm going clockwise around it this way. That means here I go clockwise as well. So where's the next group? Carbon to the right or carbon to the left? Carbon to the left, okay. So that means that group is doing what? It's going like that. It's going down. Okay. And again, trans is really easy to see in that kind of drawing style just because one's up and one's down. Right? Boat and chair give us a little bit more idea about where everything is in space, but these are a lot easier to tell. Okay. All right, so I'm going to skip some of this because we talked about a lot of this stuff. And we're going to talk about naming things, okay? So this is what I want you to do real quickly. Oh, I should have you grab a few more. I forgot we had to do all this naming stuff. Grab a green and an orange and a whatever colors you want. Okay. I'm going to grab a green, though, because green is chlorine. So I'm going to put chlorine on there. And you'll need a white. And we're going to build this molecule that's shown on the left, okay? And we're going to name it. Because right now our naming system doesn't allow us to make these have different names. They're both 2-chlorobutane. So I have my other 4 centers, okay? Or my other 3 centers. I'm going to pull a bond off of each one and then put them together like Tinker Toys so that I have 2-chlorobutane. So build the 2-chlorobutane. Should be fairly quick because I had you build them ahead of time. If you don't have one built, go ahead and build one really quick. So that is 2-chlorobutane, right? The one on the left. The one on the right is its enantiomer. I can show that it's the enantiomer pretty easily by taking 2 groups and switching them. So if I take the green and the white and switch them, right, like this. Remember what we've already done? We did a lot of this yesterday. I switched the green and the white. That automatically, whether you know it or not, or see it or not, I should say, you should know this, makes the enantiomer, makes the mirror image. And I can hold that up to the screen, and the green one's the chlorine's going in the back, right? So you see how that works? Again, reviewing, switching 2 groups gives you the mirror image or the enantiomer molecule. Okay, so I'm going to switch my carbons back, and I'm going to go back to the original. I switched my carbons now, not my green and my white. And huzzah! I just like saying that. Looks like that. Now, we have to have a way to name this. So the rules that we use are known as Kahn-Ingold Prelog rules, CIP. And the way we do it is we rank the atoms by priority. Now, hydrogen is always the lowest priority, except when you have a lone pair of electrons. So that we're going to give the number 4. Okay? So hydrogen has a priority 4. Oh, actually, and let me redraw it on the screen here, and I'm just going to do it right on the screen. So I have my molecule that looks like this. And chlorine has the highest atomic number of the bunch, right? So that's going to be number 1. So Cl is number 1. Now, I have a tie, right? You see I have a tie? The tie is I have carbon and carbon, right? So how do I break a tie? Well, it goes like you might expect. This carbon has hydrogens attached to it. It has 3 hydrogens, right? This carbon has not 3 hydrogens attached. It has a carbon and 2 hydrogens. That makes sense? So this breaks the tie. You go by the first point at which, okay, an atom has a higher atomic number attached to it. So the ties can go out a long ways in some structures, but as soon as you get to an atom that breaks the tie, and the tie. You don't have to add, like what a lot of people mistakenly do, they'll say, well, that's 3, and that's 6 plus 2, so that's, you know what I'm saying? They just add the atomic numbers, right? You don't do that. You just say, oh, first point there's the highest, which means when you write these down, you write them from highest to lowest attachment, okay? So based on that, this group gets a 3, and this group gets a 2, and this group gets a 3. Okay, so now, hold your molecule in front of you, like this, okay, and put the 4 group away from you. So it's basically you're holding it the same way that you were looking at it before, right? And then look at the rotation of the priorities, right? 1, 2, and 3. So which way is that going? So it's clockwise, right? On paper, we draw like this, and then we go like this. Let me get a different colored pen. Hang on. We go like this. And really, you only need to see where 1 and 2 go because 3 has to be in the order, has to be the other thing. So it's going to follow no matter what. But a lot of times, of course, people want to be complete, so they'll go like this. That's the direction, right? Now, if that's your car, this is the analogy, I think I might have given you this. If that's your car and you're turning the wheel of your car that way, which way are you going? Which way? Left or right? What? This should be a very certain answer. You're in your car, you turn your wheel that way, your car goes right. Okay. I didn't know this was driver's ed. I just like... This is not a trick question. Okay, so this is what I want you to do. Take 2 groups and switch them. Doesn't matter which 2. I'm doing a hydrogen and an ethyl because I'm crazy. So this is, did I put R? Yeah, I put R. Switch 2 groups. That coffee, by the way, has a ton of caffeine in it. I'm just saying. I'm so awake right now. I did get a full night's sleep. That helped. Hold the number 4 group away from you. Okay. What's 4? Still it's the hydrogen, right? So which way does it turn? There's 1 here. 2 was which group? Ethyl. So now it's going this way, right? So you notice how by switching the 2 groups, now the rotation is changing. So which way does your car turn when you do that? Left. Thank you. Man, I never had so much trouble getting you to tell me how to drive a car. Yeah, that's the enantiomer. But this is the beauty of it. When you switch to 2 different groups, you now have a way to distinguish between one enantiomer and the other. It's completely arbitrary. They could have numbered it from lowest to highest instead of highest to lowest, and then everything would have been backwards, and that would be horrible for me because I learned it this way. But yeah, it's completely arbitrary. But now we have a way to tell people it's R or it's S. So going back to the previous slide. Well, actually, previous slide. I can notate these things as 1, 2, and 3. Hydrogen's in the back. And then I go like this. And that's the R. And so I can name that as 2-chlorobutane. Right? Now, the thing that we add, or have added, okay, I'm going to have to use my finger, is the R, and a little hyphen in between. So that's R2-chlorobutane, and S2-chlorobutane goes the other way. The tip of my pen broke and fell off. Sad. I have more. I'm not going to stop. Just use my finger. So the other one would be what? S, because this is 1, right? This is 2. This is 3. Goes that way. That's R. What's the problem? The chlorine's in the back and the hydrogen's in the front. So this is the trick. This is how I'm going to teach you how to do this. Okay? That looks like it's R, right? But number 4 is in the front, so it's actually S. Okay? Your book is going to tell you things like redraw the molecule, and I will teach you how to redraw the molecule. It's a very important skill to redraw the molecule, right, in different configurations. But what's more important in naming is just being able to assign the configuration correctly and quickly. Okay? You don't want to spend all day on it. So when a molecule is drawn like the one that's here, then I would say this. Oh, that looks R. And then, but the 4 is in front. And so rather than rebuilding it and redrawing it and doing all that stuff, so it's S.
So it's basically negative R.
Just don't do that. But yes. This is what happens when you write with your finger. S. So you reverse the configuration. If number 4, like whatever you assign, if number 4 is not in the back, you just reverse what you assign. Oh my gosh, that would be so painful. I'll see that on an exam. It is kind of like that. Okay, any questions about the process? We got some ones to practice on, of course. So the rules are basically, right, rank the atoms 1, 2, 3, 4, right, on the chiral center by atomic number. Right, 1 goes to the atom with the highest atomic number. Orient 4 so that it is away from you. Now, so what I've just told you, this is kind of like book rules condensed. What I just told you is just assign the direction of the turning and then look to see where the number 4 group is. If it's in the back, the orientation you're looking at is correct. If it's in the front, the orientation is backwards. And so you reverse the configuration that you see. Okay? Negative. Oh my God. Okay, let's do this one. Oh, I still want to use that pen. All right, hey, now we're going to take a short pause. I am going to get a pen tip. So again, we assign priorities based on atomic numbers. So this is 1, 2, 3, and 4. So which way do the numbers rotate? Clockwise, right? So going from 1 to like this. Okay, so it looks what? Looks like it's... But hydrogen's in the front. So to actually get the enantiomer, right, configuration, if you were really to follow the rules, you would actually have to draw that molecule backwards in order to do that, right? So, but looks are H is in front. So that means it's actually S. We don't know how to name that. Well, we haven't gone over the nomenclature for this yet, so pass on that. But whatever the nomenclature would be is it would be S in the front, and then you would name it. Actually, did we do ether naming? We didn't name ethers, did we? No, okay. I should just throw some of that in there at some point. Huh? In this class, yeah, we haven't done ethers. Yeah. The other class we did. Okay, another technique, if that really bothers you, is before you do the assignment, make sure 4 is in the back. So the way you make sure 4 is in the back is you have to switch 2 groups and another 2 groups so you don't switch the configuration. Like if you want to redraw this, and this is actually what I'm using these slides for. If you want to redraw this molecule in a different configuration, what you do is you go like this. I'm going to draw, oops, just trying to think about the best way to do this. H and Cl, I'm going to switch those because I want 4 in the back, right? So I'm going to put 4 back here, and I'll put 1 up here now. Now, if that's all I do, then I've drawn the enantiomer. Like if I draw the rest of the molecule the same and just swap the 2, I have the enantiomer. But if I want to keep the same molecule, right, what I have to do is actually swap 2 more groups. Like that. So I swapped these 2, and I swapped these 2. So this is actually the same molecule, but in a different rotation. Okay. So if this is actually, this again, this is 1, and this is 2, and this is 3, right? It goes this way, and that's S, right? And that's what we already determined before. Looks S is the way I would have said it.
These are chiral, right?
These are all chiral, 4 different groups on a central atom. Yeah. All right.
How does something become carbon?
Oh, so how does something become R? It just depends on how the molecule is made, actually. So you.
Like you said, it's the right stars, and
Yeah.
so if it goes to the left, it's S.
So if I take just this molecule again, and I'm going to switch just 2 groups, right?
No, I understand that you're switching it and
Yeah.
stuff, but like just
Where does it come from?
No, like your simple thing, I think I just,
Oh, yeah, no. If the H is already in the back and it's going R,
Oh,
then it's
so-
R.
so if you're going right and the H is in the back,
Yeah.
you're
It's
right.
It's
then
right.
If the H is in the back and you're going left, it's S.
Yeah.
Okay,
Yeah. So as long if 4 is in the back, now this is a very important point. If the 4 group is in the back, the low priority group is in the back, whatever you see is the configuration. But if it's in the front, you still assign the configuration, but realize that you have to switch it, rather than redraw the molecule backwards. Yeah. Okay. Okay. So let's assign this one. So we're going to do 1 and 2. Well, we're just going to assign the configuration because I've taught you the rules a different way than is on the slides. Okay. Assign priorities. What's 1? What? The NH2? Why is that 1? Oh, yeah. So it's the O. And this is this is 2, right? And this is 3. I'm missing a group. What's the group? Hydrogen. So which way is the hydrogen going? Front. Now, we really want to have the hydrogen be in the back to do the assignment. Do you want to redraw this, or do you just want to do the assignment, right? So we're just going to do the assignment. It goes this way, right? Which way is that? S. Looks, but here, looks S, right? H is forward. So, forward. There's a bunch of letters in there I didn't write. Is actually R. Now, you can prove that to yourself if you want. You can build it and then turn it around, and you'll see that's the way it goes. But you can sort of imagine, okay, I'm driving my car. How this works, okay? I'm driving my car, and I'm driving it like this, right? So I'm going between the rows, right? And there's Ashley. And I go like this, which way am I turning my wheel? Towards her. Clockwise or counterclockwise? To you. Counter, but to me it's clockwise, right? So from the perspective of the front or the back, the way the thing turns is the opposite. So when you see the molecule and the group is in the front, but it's turning the wrong way, you're really like standing in front of the car watching the wheel turn. From the orientation of the driver, though, that's what we're doing it as. The orientation of the driver, when I'm going like this, I'm going to the right. To you, I'm going to the left, right? And which means you should probably get out of the way. What's that? It's not, no, I'm the one driving. I'll hit the accelerator. Sorry, didn't mean that. Let's do the, we already did the top one. Boring. Let's do the bottom one. This is, anybody know what that is? It's alanine. It's the amino acid alanine. Okay, we're going to assign the configuration to the carbon, that's chiral, which is this one. What are the numbers? Nitrogen is... Nitrogen is what priority? Which one? It's top priority. Now I have two carbons, right? There's a carbon here, and there's a carbon here. Which carbon gets higher priority? Right, so the question is, guys, the question is, isn't O higher priority than N? But you go by the thing that it's directly attached to. So just back up for a second. So this guy here is directly attached to the center, so it gets the 1. Here, it's attached to a carbon, right? So the atomic numbers, I write 6 and then 7. So this has number 1. It's either this one or this one is number 2. Which one's number 2? Left one, because these are both carbons, but this carbon is attached to 3 hydrogens, right? And then this carbon is attached to 3 oxygens. Now, why do I say it's attached to 3 oxygens? Because there's 3 bonds to oxygen. So I actually count the number of bonds that are attached. You rank those in order of decreasing atomic number, and then you make your comparisons. But, you know, when you see 3 oxygens versus 3 hydrogens, it's pretty clear which one wins. So this one's 2. That means this carbon at the bottom must be number 3. The hydrogen... I just realized all my examples are hydrogen in the front. That's probably why it's confusing. So what does the configuration look like? It looks like it's S, right? It looks like it's going this way. So that means it's actually R. Actually R. Cool. Okay, let's do this one. This is just another example of tie breaking, right? It may not happen that the tie breaks at the first carbon away, so then you have to go to the next carbon out, right? So here, you look at this, and this carbon on the right is bonded to 2 hydrogens, so this side's carbon, hydrogen, hydrogen. This one's carbon, hydrogen, hydrogen, so that's actually a tie again. You go to the next one out, and this one is carbon, hydrogen, hydrogen. That's what it's showing here, right? And this one is carbon, carbon, hydrogen, right? So these 2 tie here, but this is the tiebreaker. And so this one gets assigned 2, and this one gets assigned 3. Okay? So that's how this whole tie-breaky thing works. Same thing here, right? I have 1 and 4 are usually pretty easy, okay? But it's the ones in the middle that you have to sort of decipher. And so tied and tied, This one is bonded to carbon, carbon, and carbon, right? This one is bonded to oxygen, hydrogen, and hydrogen. This is the tiebreaker right here. You don't look at all the things that are attached to it. You just look for the first atom that has a higher atomic number. So that means the priority goes to this carbon here. Okay? Any questions on those? Yeah, go ahead.
Yeah, why is 1 next to H?
Say again?
1 is next to H and then 4 is next to OH.
I don't know. Because it's wrong. Yeah. Huh. Really? It looks, yeah, it's because it's wrong. Sorry. So much for 1 and 4 being easy. And 4's in the front again. It's not always going to be that way, so don't think you always have to reverse it. I'll have to make a few more examples. Oh, good lordy. Okay, now we're going to, again, right? So here, priority, is pretty easy to see that this is number 1. The reason it's number 1 is this carbon's bonded to an oxygen. But the way you count this is as if it's bonded twice, okay? So you count each oxygen bond. So if on this other side I had this, okay, then you would have gone to this position and said, okay, one side out, that's a carbon, that's an oxygen, oxygen, hydrogen. This side is carbon, oxygen, hydrogen, hydrogen. So again, this point here is carbon, oxygen, sorry. How do I want to do this? Let's see. Yeah, just the list for this carbon is oxygen, hydrogen, hydrogen, like that. This side, even though there's one oxygen on this side and one oxygen on this side, right? This side wins because it's bonded twice to that oxygen, okay? So the tiebreaker, if it's like this, let me erase, that looks like I meant to put, I didn't mean to put an oxygen there. I was just circling it. The tiebreaker is here. Okay. So that's how the priority works out. Okay, let's do RRS for the next molecule. Yay. So I have a carbon here. This is the one I'm trying to determine the configuration of. And I'm laughing because hydrogen is in the back. So this is 4. This is 1. Which one's 2? What's that?
What is the carbon on the right double bonded?
Carbon. Yeah. I know that looks weird. You usually see an oxygen at the end of that. You're so used to being like, oh, that's an oxygen. But no, there's not. It's just double bonded carbon to carbon. So what's the priority of the group on the right? 2 or 3? 2. And the one on the left is 3, right? If you look at, but it looks exactly the same, right? This is a carbon. For this carbon, right? It's a carbon bonded to carbon, carbon, and hydrogen, right? For this carbon, where I have the number 2 written, it's a carbon bonded to carbon, carbon, and carbon. And so the tiebreaker is down here. Okay. Yeah, it can get like, At some point, okay, I would just tell you, I don't do any of that at all, and I still get it right. Because at some point, you learn to look at it and say, oh, it's got a double bond to something else. And you realize that that's going to be the tiebreaker at some point. But for now, what you should be doing is giving the lists of how you break the ties until you get used to doing it, okay? Okay, I'll skip this one. I made this an extra slide in case I wanted more examples. I can come back to it if you want. So here's albuterol again. We're going to show how it's R or S, okay? The chiral center is here. I am missing a group, which is the hydrogen, so that's in the front. On the enantiomer, the hydrogen's on the back, like that. So we're going to assign priorities. So this is, oxygen is 1, right? What is this carbon going to be? 2? So this is a carbon bonded to hydrogen and hydrogen, right? So this is carbon, hydrogen, hydrogen. What's this? Carbon bonded to carbon, 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 right? So this is carbon, hydrogen, hydrogen. This one is carbon, carbon, and carbon because of that, the double bond on that side and the single bond on that side. So the 2 priority is given here, and this is the 3. Okay? If that bend hadn't been there and it had gone straight to the nitrogen,
But then that's R.
oh, is it? 1, 2, 3. It's R. Yeah, it is. Huh. I wonder if I had the labels wrong or did I do the assignment wrong? I think I did the assignment right, though.
Is it because 3's connected to nitrogen?
Yeah.
Oh, that's right. That's right, right. 2's connected to carbon. 3's connected to nitrogen. Sorry, yeah, you're right. So this is carbon, 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 but this one is nitrogen, hydrogen, and hydrogen. Yeah, that's right. So that is number 2. All right, I got it wrong. So what is it? All right, it's S, it goes this way. And then this one is the enantiomer, so it's just flipped, right? So you can automatically assume that one's R. The assignments would all be the same, but the hydrogen would be in the front instead. Okay, that's just a summary slide. I'm going to just leave that for you guys to read. Hang on. Optical activity. So this is R carbone and S carbone. That's the caraway and mint. And you notice their melting points and their boiling points are exactly the same. So if you have a sample of a chiral compound, and it turns out when you make compounds, like synthesized compounds, a lot of times there are methods for trying to make one enantiomer in preference of another, okay? Question is, how do you tell how pure your product actually is? Or if you have a mixture, how do you tell how pure your product is since all the physical properties are the same so far? Right? You can't do it by boiling point. You can't do it by density. You can't do it by index of refraction. The only thing it turns out that happens is that they interact with light differently. And so I started talking about this a little bit the other day, but let me go ahead and go into this. So when you have light, it's an electromagnetic wave, right? And as an electromagnetic wave, it travels through space. And the electric field and magnetic field are said to be at 90 degrees to each other, orthogonal to each other as they travel through space. That's really confusing for a lot of people. So just pretend it's the simple wave, single wave traveling like this, okay? Now, normal light doesn't have a preferred orientation. Because when you look at the sun, okay, the waves are traveling not only in this direction, but in all directions. And it's pretty uniform the way it travels down from the sun. So you have waves in both the horizontal and vertical orientation, and then all orientation or vectors that can go in between horizontal and vertical, which is all vectors can go between these angles, okay? So light's traveling, but if you take a polarized piece of glass, so where do you hear the word polarize? What kind of glasses? You ever? The sunglasses, right? You get polarized sunglasses. What polarized sunglasses do is they filter out for just one orientation of light. And if I remember right, it's this orientation that comes like this. And the reason it's effective, it's easier for me to draw this here, is when light comes down like this, okay, or the light waves come like this, okay, these ones will reflect off the surface and create glare. So when you look at the surface of water and you see the reflection of everything behind it, it's actually mostly one polarization of light that's reflecting off the surface of the water and then coming into your eyes. The rest of it travels in through the surface and goes down into the water and then reflects off things in the water. So who here fishes or likes to fish? Do you have pairs of glasses that you wear when you go fishing? Right? Do you wear, yeah, polarized sunglasses is what you wear when you go fishing. Why do you wear polarized sunglasses when you go fishing?
So you can see past the surface better.
It allows you to see past the surface of the water because the way the polarization is set up is it blocks all the light rays that are coming this way to your eyes, and so you only see the stuff that's reflected from the bottom of the pond or the pool of water. Same thing is true when you're driving in a car. Polarized glasses are good because the light comes off the road. The road glare and the glare off the windows is the same as the light reflected off the water. When you put polarized glasses on, it blocks that polarization of light, or tries to block that polarization of light. So here's an interesting thing. And you don't need polarized light actually to do this, but it's how we measure it. When you take a solution of one enantiomer, okay, one of the pair of chiral molecules, and you pass light through it, okay, the light turns. Think about that. It's weird to think about. Like, the light that goes through, right, a pure enantiomer will turn either to the left or to the right. That's how chiral compounds can be, like the enantiomers can be resolved, or you could tell like whether or not you have one enantiomer versus another, okay? It actually takes the light and begins to turn it. Now, the R, let's say R turns the light to the left, okay? Then S will turn light to the right. So the enantiomers have the same influence on the rotation of the light, okay? But they turn the light in opposite directions and by the same amount. So in that respect, they're still the same. So we think of one as the positive rotation and one as the negative rotation. Okay? So the way we can actually see this when we're analyzing chiral compound, okay, and I'll re-summarize all that stuff I just said, is that we use two polarized filters, right? So it's like taking two polarized lenses, and we put them front, like one going one direction, okay? And typically, we turn the other one the other direction. So think about it like this. If I have a polarizing filter on the front, okay, and it's turned in this direction, right, like this, right? And then I take another polarizing filter and I turn it this way. So originally they're both the same, right? Lights can go through. And then I turn the other one this way. So I have one polarization being blocked this way, and I have one polarization being blocked this way. What do you think you see? You see black. It blocks all the light, okay? So we take two polarizing lenses, okay? And we have them set up like over here. This is one going this way. This is one going that way. when you look through there, what you're going to see is just complete darkness. Okay? And then what we do is this. We make a solution of the chiral, one of the enantiomers, or a mixture of enantiomers, and we stick it in a glass tube, and we stick the glass tube between these two lenses. Right? What'll happen is that light, this is a weird thing about polarization. When you put another polarization inside between the two polarizing filters, that causes the light to turn a little bit as it passes through, and now it'll get through the filter that's in front of your eye. And so you will see some light getting through the filter. So now you see a little bit of brightness. To figure out how far the light's rotated, you just rotate the back lens or the front lens, but usually we rotate the back lens because it's in front of your eye. You rotate the back lens, the one in front of your eye, until it gets completely black again. And then you measure the number of degrees that the light is rotated. Okay? So imagine you're looking at it like this. Okay? And your eye is like this big relative to that spot. Right? It's going to be completely black, and I'm not going to color it because it's a blackboard, so it's black, right? And then what you're going to do is you're going to put a tube of material behind this lens, and then what it'll happen, it'll look like that. It's just uniformly lightly lit. I don't know if that's it right. Okay. Then you're going to take this thing, right? Now, 0 degrees is here, all the way around, right? That's 180. This is 90, right? And there's actually a line here, and this eyepiece can be turned different numbers of degrees, and you can measure the number of degrees. If it goes this way, it's plus. If it goes this way, it's minus, okay? And it's plus a certain number of degrees, minus a certain number of degrees. The number of degrees is when you turn this thing, eventually the light will go back to being black, or as black as I can get it to be, and maybe it'll be over here, okay? And that would be, let's see, 30 degrees or so. We would measure that as a 30-degree positive rotation, okay? So that's a plus rotation. Minus rotation is from your viewpoint as it goes to the left. If you have, let me see something really quick. So this is kind of what this drawing is, okay? And again, the observer is behind that rear lens. I really wish they'd have drawn it this way because it kind of makes more sense because then it would be coming towards you. So plus is to the observer's right, clockwise direction. Minus is the observer's counterclockwise observation. So if you have a pure compound, so let's say you have R, and it's, let's say, minus 3.8 degrees, okay? The S, and again, if it's pure, will be plus 3.8 degrees. It'll be exactly the same, but in the opposite direction. Now, let's say I took a 50-50 mixture of R and S and mixed them together. Think about what's going to happen to the light as it comes through a mixture. When it hits an R, right, it'll go this way. Well, it'll go like this. When it hits an R molecule, it'll turn the light that way. When it hits an S molecule, it'll turn the light that way. What'll happen in the end, though, which is a 50-50 mixture? What's that? Yeah, it'll be black again. What you'll see, it won't actually have any optical rotation. So it turns out like if you have an equal concentration mixture of enantiomers, right, the optical rotation will be 0. We call that a racemic mixture. That's a mixture of equal concentrations of enantiomers. Oops, shouldn't have written all over this slide, but I did. Well, that, okay, so the degree of rotation depends on its relative concentration. Okay, there is no way, remember the way we assigned R and S, it was kind of arbitrary, right? R and S doesn't necessarily tell you if it's R that it's always going to the left or always going to the right. That's actually dependent on how the molecule interacts with the light, not with how we name it. But we do know if it's R and it's a positive rotation, then S will have a negative rotation. Okay, so they're always going to be, R and S will always be opposites of each other. We just don't know whether R will always be to the clockwise direction or the counterclockwise direction. Okay, so now, sample concentration is important in the way the light rotates. So if you have more material dissolved, right, then the light will rotate more because it interacts with more molecules as it passes through the solution. How far the light travels through the solution also determines how far the light will rotate. So if you have a concentration solution, okay, in a tube like this, or the same concentration in a tube that looks like this, right? Because there's more molecules for the light to pass through here than there are here, the light rotates more. So the amount of rotation is dependent on two things, okay? Concentration the path length and what we call the specific rotation. You can think of it like as density, right? Density is dependent on mass and volume, right? And then we have or specific heat. When we talk about heat capacities, the amount of energy is dependent on mass and change in temperature. It's that kind of thing. To calculate the specific rotation, we use this equation. This is actually the observed rotation. I don't think I have. I didn't notate these things at all. Observed rotation. This is path length. And this is concentration. So, path length, I don't know why they do these things like this, but path length is measured in decimeters. What is a decimeter? Anybody know? We hardly ever use it. It's 10 centimeters. So it's the, yeah, I don't know. Why didn't they just use centimeters? They didn't. Okay. So path length is measured in what we call decimeters, and that 1 decimeter is 10 centimeters. The concentration kind of makes more sense. It's the grams dissolved per milliliter. Okay. Now, if you have a pure substance, what is grams per milliliter units of? What do we, grams per centimeter cubed, grams per milliliter, what do we usually attribute that unit to? Density. So if you have a pure compound and you put it, and rarely do we use pure compounds in a tube, but if you have a pure compound and you stick it in a tube, right, it's the density of, the concentration is its density. So this is really the density of the solution. And for pure substances, if you have enough of a pure substance that you can do this, then it's actually the density of that solution or that liquid. Okay. When we do this, I don't know if we'll do it in the lab. Probably get around to it someday, just kind of having it out for people to play with. We have enough carbone of each type, each enantiomer, that we can have a tube completely filled with it. But normally you don't do that. Okay. Now, specific rotation is dependent on both the temperature and wavelength of light. Okay, and it can be very sensitive to temperature. You can have large positive rotations at room temperature, and then when you heat things up, they'll have large negative rotations. So it is really important that we always report what the temperature and the wavelength of light is. Now, the way it's done, and I'll show you on the next slide how temperature and wavelength are shown, is like it is here on this slide for 2-bromobutane. 20 is the temperature in degrees Celsius. And D, they could have just said 589 nanometers. But it's 589 nanometers from a sodium lamp. So we actually have a special lamp. It's got sodium, the elemental sodium as one of its electrodes, and that's how it generates the light. You probably have seen sodium vapor lamps before, because a lot of the street lights, those yellow light that you see, those are a lot of those old ones are sodium lamps. Okay, so we use a sodium lamp. We look at one specific wavelength of the sodium lamp, and that sodium lamp line is called the D line. Okay, but it's 589 nanometers. So this is the wavelength of light down here, and then down here I reference what that means. Okay, 589 nanometer wavelength. The plus and minus again refer to rotation clockwise and negative would be rotation counterclockwise. And again, that's from the viewer's perspective on the polarimeter, whether it goes to the right in your eye or goes to the left. So literally when you have this knob, if you turn it to the right, the clockwise direction on the instrument, that's plus, and turn it to the left, that's minus. Okay? All right. Questions? It's like all brand new stuff, right? Most of you have not ever seen anything like this. Okay. A couple other notes. There's no relationship between RS configuration and the direction of light rotation, plus or minus, except that they're always opposite. R and S always have opposite rotations. Okay. And here's an example of, we'll skip the RS configuration of the amino acid, but this particular compound, this is aspartic acid, I think, or glutamic acid. I always forget how many carbons each one has in the middle. But at 20 degrees Celsius, it's a negative rotation, and at 100 degrees Celsius, it's positive rotation. So again, temperature is very important. Couple other notes. We actually have calculations. I'm going to skip the calculations today, but we'll start those next time. And we'll keep the model kits together, just put them back on top, and then we'll stack them up over here. Just a little summary. Only chiral molecules are optically active. Okay. Optical rotation is only determined experimentally. There's not like a simple calculation for it. They're working on the calculations now, But it involves like the wave functions for the orbitals of the molecules, and those are really difficult calculations. Racemic mixtures, right? Equal amounts of R and S have zero rotation. And then we'll skip that question. You can look at it though. What is the optical rotation for 2-methylbutane? I'll draw it for you real quick. What is the optical rotation of that? Zero, because it's not chiral. Right? And you be careful because sometimes people will draw them like that and say, what's the optical rotation of that? And then they try to assign R or S, and it's like, it's not really chiral because there's 2 methyl groups on there, so, yeah. That's like a standardized exam question. All right, we'll do the calculations next time.